Okay, welcome back. This is now part 2 of HSMWorks tutorial. So in this one, we'll also be doing some more sheet metal toolpath generation for our CNC. So this time, last time, if you recall, we generated a toolpath for an elevator gusset that was 1/8 inch thick. For this one, we will be doing another part from our 2018 robot, and this is a slightly more complex part, and it is part of our elevator gearbox plate. One of these. I'm actually going to make this with the top plate. Okay. And fix it. So now this part right here, you can see we have a ton of different sizes of holes. So these ones here, these are 4mm. So these are smaller than 3/16. So for these, you're going to want to leave those as center drill holes. And then the rest of these you're going to drill out. These ones, these three here, these are also smaller than 3/16. These are supposed to be tapped to 1032. And then we also have this feature here, which was where the flange of a bearing set in. Now for this part, another thing that separates it is there's also, this one has configurations to it. So we have the motor mounting plate, and then we have the mounting plate, the larger one. So I'll just be doing 2 of these. So when you have these, right, you're going to want to mate them to the same level. Since these are both flat sides, we're going to make them like that, and then I want about 1/4 inch in between my parts. Now once again, I'm going to, just like last time, create a sketch and draw out my stock boundaries. So this time I'll draw this way. So I've got 48 inches that way and 12 inches this way. Leave about 3/8 of an inch here and 3/8 of an inch there. Yep, there you go. Just like that. And then I'm going to create a 0, a coordinate system signifying where the center is. So x-axis is the short side, y-axis the long side, z is vertical, just like that. And then we create a job, these two in the coordinate system, just like that. And now we're going to center drill every single hole. Once again, tool library, we'll be using the 3/16 center drill. Everything here I keep default holes, just like same diameter. Make sure you get all the holes since there's a couple different sizes. And also one thing, you can only do select same diameter if you select the actual cylindrical face. Otherwise, if you select the edge, you won't be able to do same diameter. So as you can see, I've got all of my holes there. For layers, once again, we're going to go from the top of the model, and we're going to want to go down 50 thou into the part for the center, just like that. Next step, let's name this first. So I'll call this 1 center drill. And the next step, we're going to want to drill all the 3/16 holes, or all the 3/16 or larger holes. Any of the smaller ones we do not want to drill out. Those will be drilled out on the drill press using the correct drill bit size. These right here, these are smaller than 3/16. We'll do those as well. The rest of these holes, I believe those are all smaller than 3/16. And you just check. 3/16 is 0.875. So see that one's 0.1590, and this one is 0.1772 or 4mm, which is smaller. We're going to need this to drill all the way through. So come here, drill tip through bottom, breakthrough depth 0.1 inches. One thing you can just verify is, so the green, that's the path it takes, and then the blue right here, you can see it's actually higher than this if you because the circle signifies where the drill bit is actually like the correct diameter, since the drill bit is tapered. if you were to plunge with an end mill, this green dot at the point would not extend past the circle because the end mill is flat. Now I'll name this 3/16 drill. And then we're going to want to cut out all the inside. You're going to want to cut out all the inside contours first, and then cut out the outside, because that improves part, stability in a sense. Keeps the part makes it harder for the part to fly out if you cut out the insides first. So the tool we're using is a 3/16 flat end mill. We're kind of slightly thicker materials, so you're going to slow the feed rate down. So you have the ramp feed rate, that's the ramping down. I typically like to keep these two the same. And these feed rates, they're not permanent in a sense, so the CNC operator can manually override up or down the speeds. I'm going to just select all my contours. So I really do wish HSMWorks had some sort of ability to be able to select all these interior contours, but this feature does not exist. So on larger parts like the belly pan, it may take 10 minutes to select all of the cutouts. And always remember that you need to keep the arrow on the side that you want to cut out. Now for this part, it is slightly more dangerous in a sense to go contour, since it's a 1/4 inch thick, which is pretty thick material. It's about as thick as we go for our parts typically. And you have these giant chunks which will come flying out. So CNC operator will usually there would be 2 people, usually one person on the coolant and another person on the vacuum, to suck these large chunks right out as soon as they get cut through with. So now this part, I recall it takes about 20 minutes per plate total, which is fairly quick considering how large of a gearbox plate and how complex it is. And the reason why we do more than one plate at a single time is because that allows us to avoid having unnecessary tool changes, since tool changes take up a lot of time. Since the CNC operator has to go change out the tool, loosen the collet to change out the tool on the router, and after that they have to re-zero the z-axis of their tool. So here we go, we have all the interior contours selected. Next, you're going to remember that we have to go bottom, so about 30 thou down from bottom contour to cut into the MDF board to ensure that all of these are properly cut out. And then we're going to want to head here to multiple depths. So 1/4 inch, you won't be able to cut all the way through. Instead, we'll want to take 3 passes. So 1/4 inch plus the 30 thou that we added extra on the bottom. So this 0.28, that's the total depth it has to cut, and then we'll just divide that into 3. And once it finished shadowing, you see you have 3 distinct layers. However, you also need to ramp this. So you head over to the ramping settings. We're going to want to ramp, start 20 thou above the surface of the part. For these are interior, so you can keep the lead-in, because the lead-in it'll sort of, instead of going straight up when it's done with the cut, it'll curve inward, and it's okay because if it curves inward, because there is no material here anymore, it's just air. Versus if you were to lead out on the outside, it would be cut a full depth of cut straight into the rest of the stock, which is bad. And here we go. You see, rename this 3/16 end mill. And then afterward, we're going to want to cut out the outside. So do another one of these 2D contours. Select the outside edge, just like that. Same thing with the depth. We want to go 30 thou down. Multiple depths once again. So 0.25 plus 0.03 divided by 3. And then we're going to want to ramp it again. And at 20 thou above the part. And like I said before, if you're cutting exterior, you're going to want to disable lead out. Just like that. And then we're going to name this, say, 4/316 end mill. So then you can highlight all of them and then simulate them all together. Show stock. So you just want to verify everything is done properly. So you have center drills for all of the holes. Oh, actually, it looks like we missed one hole here that we did not make a center drill for. So we'll have to remember to go back and fix that. Just to make, and then we want to make sure all the pockets get cut out. Looks good, and the contour cut out. So remember this hole, we need to fix that. So we'll head back over to center drill and select this hole. And then afterward, we just export. So post-process. So you're going to post-process this as one center drill, put it on the flash drive. You're going to post-process this as 3/16 drill on the flash drive. And then for this one, you can actually, since there's no tool change or anything necessary to do in between these, since it's the same tool, you can actually highlight both at the same time and then post-process them together. And we'll call this 3/316 end mill, and it'll post together. That way, there's no stop between cutting the insides and the outsides. But the reason why we separate them is because if we put these both in the same 2D contour operation, then it may cut the outside before the inside, or do a mix of cut the outside and then cut some of the inside, cut some of the inside of this, cut some of the outside of that. So splitting them up just ensures that this operation will happen first, the insides, and then the outsides. And there's actually one last one we forgot. It's this sort of indent here. For this one, we'll also be using 2D contour. Now, if this surface right here were larger, you would want to use adaptive so that you can clear out the entire area. But since it's smaller than the diameter of the end mill, we'll just use 2D contour. So just like that edge right there. And then you can do a single pass for this. And so this lead in, we're going to want to lead in from the interior here. So I'm going to set the lead in distance to say 1/4 inch. And then we're going to ramp this as well. Actually, because it's so little, we don't really need to ramp it. And just verify this proper tool. So you see it leads in from the middle, goes in, and then takes a cut all the way around, and then leads back out. And we're going to want to do this after it cuts the large chunk of the material out here, but before it cuts the outline out. So this will actually be called 4/316 end mill, and this one will be called 5/5 operation. And then once again, select all three and post all three at the same time. And that's it for part 2. Part 3, we will be talking about using vices. Since we have a vice set up on our CNC to cut tube with, and that was actually inspired by how Team 1678, HSMWorks, how they cut their tube. Here, I'll show you. So a quick picture of the tube jig. So this was the tube jig in the CAD, and we actually cut this out on the CNC router itself, and these are little machine shop screwless vices. So here's cutting it out, and each of these, they have slots in them, and then they have holes that are tapped for these vices to be held down. So there's 2 screws, and then we use a test indicator to line up this bar first, since one side is actually machined flat, and then we indicate each of the vices. You see in here, this was our V1 intake, so this is holding in. It's really great for cutting drive tubes, because you can do it all in one pass essentially. Previously on our manual mill, we would have to flip the tube around, and that leads to a buildup of tolerances, which is bad. So thank you for watching.